Hi team, we're now ready to start section 3.1, complex numbers. Now, a few reminders before we start. Real numbers, or the real number system, includes rational and irrational numbers. Remember, rational are numbers that can be written as a fraction, which means they have finite number of decimals, or the decimals have a pattern that repeats. And irrational numbers are numbers like pi or the square root of 2 that have infinite numbers after the decimal. A couple of other reminders is that the square root of, say, 4 squared is 4. Remember, the square root and the square, they undo each other by definition. In the real number system, the square root of -1 is undefined, because there's not a real number that if you squared it, it would give you a negative number. Also, a couple of reminders about some exponent rules. If you have x to the n to the m, in other words, a power to a power, we multiply exponents. And if we multiply like bases, we add the exponents. Last quick reminder is a word called conjugates. You may remember those when we were factoring difference of squares. Conjugates are basically binomials that have the same base numbers, but the sign in between is different. So if we had x plus a, the other binomial would be x minus a. So let's focus on complex numbers. Complex number system includes all of the reals that we've worked with forever, include real, but now they also include imaginary. So now we have to define an imaginary number. We use the letter I, and that imaginary I, number I, equals the square root of -1. Now remember, in just the real number system, that square root of -1 is undefined. So in the larger number system, the complex, we've now added this new definition. So the format of a complex number is always a and either plus or minus b times I. It will always be separated, where a represents the real part of that complex number, and bi represents the imaginary part. So we can simplify some of these square roots in terms of complex numbers. So for example, the square root of a -81 is the same thing as saying the square root of 81 times the square root of -1. The square root of 81 is 9, and the square root of -1 is I. So we can go directly from the square root of -81 and rewrite it as 9i. Now, a quick reminder on reducing square roots. Let's take a look at the square root of -32. It's not a perfect square. So if we think of just the square root of 32 for a second, we'll scratch work over here on the side. 32, if we broke it down into prime factors, we have 2 times 16. We could technically stop there, but 16 is also 4 times 4, and we could technically keep going. But really, when we're looking at square roots, remember it undoes squares. So the square root of 32, I've got 4 times 4, the square root of 16. So that means that 4 can come out. that this 2 here does not have a pair. It's not being squared, so he has to stay inside that square root of 4 rad 2. So if we're focusing on part B here, with the square root of negative 32, we can write that as 4 square root of 2 with an I. Notice that I is not underneath the radical, plus the square root of 49, which is 7. But remember, we always write it in A plus BI form. Okay, so the imaginary is always written second. So we can rewrite this at 7 plus 4 times the square root of 2 times I. So in this example, 7 is the real part. The 4 rad 2 is part of the imaginary part because it's being multiplied by I. Now, we do not want to write the square root of negative 1 in any of our final answers. It's either going to be a real number or we're going to write it in terms of I with the imaginary. So the nice thing about I, we know that he equals the square root of negative 1, but again, we don't want to write the square root of negative 1. So if you see just I, leave it alone. Just rewrite it as I. But notice if we have I squared, that means we are taking the square root of negative 1 and squaring it. So if you were to square the square root of negative 1, technically that just leaves you with your radicand, which in this case is negative 1. If we were to take I cubed, that's the same thing as I squared times I. Well, we know I squared is already defined as negative 1 times I, so I cubed is a negative I. We can also write I to the 4th as I squared times I squared. Both of these equal negative 1, and negative times a negative gives you a positive. Every I taken to any exponent will reduce to either I negative I or 1 and negative 1. Because any number past I to the 4th can be written as one of these guys here. That's pretty cool, right? So think of all of these. This guy at the end is the nicest form to deal with. Possible, we want to write it in terms of I to the 4th power. We have I to the power of 412. I want to know if 4 will divide into 412. And it does, 103 times. So that means I can write I to the 412 as I to the 4th to the power of 103. Because remember, if you add the power to a power, we multiply. Well, I know I to the 4th is 1. And 1 to the 103rd power is still 1, no matter how many times you multiply 1 by itself. Now, I to the 27th. 4 does not go evenly into 27. 4 goes in there 6 times with a remainder of 3. So that means I can write I to the 27th as I to the 24th times I cubed, which is I to the 4th to the 6th times I cubed. Because 27 is not divisible by 4, but 24 is. So that is 1 to the 6th power times, and remember I cubed is negative I, so that just gives us negative I. Very last one is I to the 6th. We can also write that as I to the 4th times I squared I to the fourth is 1. I squared is -1. So that gives us a -1 as our result. So if the number is large, as we did here in the first example, we can divide by 4 and try to determine what that exponent would be. If it's not as large, like 27, we can still divide, or we can go straight and know 27 is not divisible by 4, 26 is not, 25 is not, so the next lower number is 24, and that leaves us with an extra 3 to make up those 27 i's, and then rewrite it as the power of 4 so we can reduce. Addition, subtraction, and multiplication of complex numbers work the way we're used to, like polynomials. Just don't forget to reduce your final answer if you have I to some exponent, and also to write it in the proper format, which is a reminder, the real part first, plus or minus the part with the I second. So in the first example, if we were to distribute, 4 times 3 gives us 12. 4 times a positive 2i is plus 8i. Negative 5i times 3 is a negative 15i. Negative 5i times 2i is a negative 10i squared. So we're still going to combine like terms in the middle there. So we have a 12. 8i minus 15i gives us a negative 7i. And remember that I squared is the same thing as -1. So since that 10 is being multiplied by an I squared, then it's still going to be multiplied by that -1. Don't add in an extra minus sign or a plus sign. The operation has to stay the same. If it's multiplication here, it has to be multiplication there. That's a common error that I see a lot. So that gives us 12 minus 7i plus 10. And combine our like terms, which are the constants, we get 22 minus 7i. The real part is first, the imaginary part is second. In our second example, we are subtracting, not multiplying. So our first parenthesis doesn't change, 7 minus 10i. The second parentheses, we distribute that negative. So we get a minus 3 minus 5i, and then combine like terms. 7 minus 3 is 4, and we get a negative 15i. Now, if you see a notation such as a plus bi with a line over it, that represents conjugate. So it's telling us we want to find the conjugate. Remember, the conjugate is the same complex number, it just has a different sign in the middle. They're being tricky with us on this first example here. They put 5i minus 7, but this is not written in proper format. Remember, the proper format always has the real part first, so the -7 goes first, and then the positive 5i would go second, okay? We have not found the conjugate yet. We have just rewritten it in proper format. So the conjugate would be -7 minus 5i. Notice the only thing that changes is that middle sign, not the sign of the real part. Our next example just has the imaginary part, a -4i. That is the same as saying 0 minus 4i. And so the conjugate here would be 0 plus 4i, which is just 4i. Notice as soon as I found the conjugate, that bar over the top disappears. In other words, we don't need it anymore. For this last example, we just have a real number. That is the same thing as 8 plus 0i. There's no imaginary part there. And so if we took the conjugate, 8 minus 0i, it still equals 8. So the conjugate of a real number is just itself. The last piece of information that we're going to work with is division of complex numbers. So we showed how to multiply them and subtract them and combine them, add them. But when we're dealing with division, we're going to use conjugates. Because remember, we want the real part plus or minus the imaginary part. The entire number is not a fraction like the two examples that we have. We have to split them both up into the real part separate, plus or minus the imaginary part separate. So what we can do is multiply both by the conjugate, top and bottom. So if I is the denominator, we're going to multiply top and bottom by its conjugate, which is negative I. And that means we have to distribute it to everybody in the top and everybody in the bottom. So if we distribute it here, we would get a negative 3i. And negative times negative would give us a positive 5i squared. And then the denominator would give us a negative I squared. Now, we need to get rid of those I squares. So that would give us a negative 3i plus 5 times negative 1. Remember, I squared equals negative 1. And then a negative I squared is negative 1. So that gives us a negative 3i minus 5 over a positive 1. So putting that in the proper format, everything dividing by 1, so we don't need to put the 1 in the denominator, but my real part is the negative 5. My imaginary part is the negative 3i. On our second example, remember we don't want a denominator, so we're going to multiply top and bottom by the conjugate of that denominator, which is 3 plus 4i. So when we distribute on top, we would get 15 plus 20i plus 18i plus 24i squared. In the denominator, we get 9 plus 12i minus 12i minus 16i squared. So remember, we need to replace all of our I squares with negative 1. So in the top, we would get 15 plus 38i plus 24 times negative 1. The denominator is 9. 12i minus 12i is 0. And then we get negative 16 times negative 1. So we have 15 plus 38i minus 24 over 9 plus 16. 15 minus 24, what is that? Negative 9. Negative 9 plus 38i over 25. So you might think we're done now because we no longer have an I in the denominator. But again, we need our real part separated from our imaginary part. So once we get a constant in the denominator, we just write it as two separate fractions. Negative 9/25 is our real part, plus 38/25 times I is our imaginary part. All right, gang, that is it for 3.1 complex numbers. Remember, if you have any questions, don't hesitate to contact me through the inbox or come and see me during my office hours. Bye.